All right, you ready?
Very good.
My name's Stephen Goodman. I'm on the Aqua team along with Sonia and Sergi. We're a part of the current system, and this is our presentation on steady state and step response. So here's a, you can see here, this is, it's just a list of kind of the stuff we're going to go through. We're going to go with a brief description of our system. We're going to go over the steady state, operation, step response, and then draw some conclusions at the end. Here's an illustration of the control system. You can see here the operator inputs the data into LabVIEW, which then outputs into the equipment. The equipment then sends it back into LabVIEW, which outputs it into data files and into plots through spreadsheet programs. This is the best diagram I could find for our system. Obviously, we're no longer the voltage system, we're the current system, so some of this stuff might not be the same. I don't know. But anyway, our generator, which is not pictured here, our generator is connected to a light array, which is our dummy load. Here's a block diagram of our system. You have the manipulated variable, which is our input in percentage, goes through the system, through the transfer function into the output, which is measured in amps, which is our control variable. So here's an example of our steady state operation graph. You can see here our input was about 63%, which resulted in an average steady state output of 1.51 amps with an uncertainty of 0.02 amps. And so then from that, we were able to form our steady state operating curve. As you can see here, our data from this point, as I believe Khan pointed out in his presentation last week, started to get a little squirrely at different extremes. But if you'll notice here in the middle, it operates on an ideal linearly, rather. So therefore, we broke it up into three different sections. We have our upper, middle, and our lower section. And we use that to evaluate our step response. Here's an example of our step response. This is a step up. We started out, as you can see over here, at about 47.5%, up to somewhere around 59% with the corresponding outputs. So, as Dr. Henry already mentioned, that stuff's boring. That's boring and not interesting. We're just concerned about this point right here. So, zooming in on this, this is an example of the Fit2 method that Dr. Henry loves. So, as you can see here, from the steady state right here of our output to the steady state of our input before the step is our delta C. Delta M is the percentage change, and then our gain was calculated by the delta C over our delta M. So here are our different sections. We compared the gains from our lower. This is our lower section down here, from 0.5 to 1 amp. This is 1.5 to 2. I'm sorry, 1 to 1.5 amps, and this is 1.5 to 2 amps. As you can see here, had a little bit of uncertainty here. That's probably due to, as you noticed on the steady state operating curve, it started to get a little, there's a lot of variance up in the upper region. Our dead time comparison followed along. It seemed fairly, it seemed to operate at the same dead time across all of our ranges for the most part. Here's our response time, or time constant rather, for all three sections: lower up, or lower down, middle up, middle down. So in conclusion, we have an operating range of 32 to 70% input to get a 0.5 to 2 amp output range. Our average step response results were, our gain was 0.042 amps plus or minus 13 thousandths amps per percent input. Dead time was 99 thousandths plus or minus 57 thousandths seconds. And our time constant, as you can see there, was 108 thousandths plus or minus 27. And as Dr. Henry put on his template, we were ready to move on. With that, any questions?